Hello scholars, today I am going to walk you through how to do this example calorimetry calculation. So just to start off, the equation that we use for all our calorimetry calculations is going to be Q equals mc delta T, where Q is the heat transferred, M is the mass of the substance, the specific heat of the substance, and then the temperature change of the substance. If you look here, I've drawn a little diagram of the example problem. So in this diagram, we have our iron and all of the information about the iron. So from the problem, we know that the mass of the iron was 100 grams. The initial temperature was 94 degrees Celsius, and then the specific heat of iron, and this is something we just look up on the internet, is 0.45 joules per gram degree Celsius. So that is how much energy it takes to raise the temperature of iron by 1 degree Celsius. And then over here in blue, I have all the information about the water. So the water had a mass of 175 grams, according to the problem. Again, the specific heat of water, which is a known value we can just find by doing a Google search, is 4.18 joules per gram degree Celsius. And then the starting temperature of the water was 25 degrees, and then the final temperature of the water is 29. Now you can probably see a little orange shadow behind the 29. That's because of that idea of thermal equilibrium. So when I take this 94 degree piece of iron and put it in this water, if you leave them there long enough, the iron and the water will become the same temperature. And that's our final temperature of 29 degrees. So we're going to start off by calculating we can do it either way. We can do the water or we can do the iron. We're going to start with the iron just because that's what I decided to do. So we're going to calculate the heat lost by the iron. I'm going to start off, it's going to be Q equals, and then the mass of the iron, which is 100 grams, times the specific heat of the iron, 0.45 joules per gram degrees Celsius. And then finally the temperature change, which is the final temperature. So delta T, remember, is TF minus TI, or the final temperature minus the initial temperature, is 29 degrees minus 94 degrees. And that's all degrees Celsius. Okay, so then I literally will just go, you can do one step where you take 100 grams times 0.45 joules per gram degrees Celsius times, and then let's see, it's 29 minus 94. Let me grab my calculator. I always recommend using a calculator because you have access to one no matter what, and sometimes you make little mistakes with your mental math that cause you to get the whole answer wrong. So it's always good to just check yourself with a calculator. So I have 29 minus 94, which is negative 65 degrees Celsius. Okay, so then let's go ahead and multiply these all together. And if you just multiply those all together using your calculator, you will get the number 2,925. Now, what is the units of this? So this is where we do our dimensional analysis. So what we have here is we have grams on the top. Remember, this is like over 1. And then we have grams on the bottom here. So we can cancel that out with that. And then we have degrees Celsius here and degrees Celsius on the bottom. So those cancel out, and we are left with joules, which makes sense because we're trying to measure energy, and joule is our energy unit. I'm always in the habit of boxing my correct answers. That's a thing that I picked up and just kind of never let go. So that's the answer there for the iron. That is how much energy. Oh no, I did something wrong. What did I do wrong? The answer is not 2925. It is negative 29.25. And that negative tells us this is heat lost by the iron. Okay, so that is one way you could calculate this. Now, oftentimes in a calorimetry experiment, we don't conveniently know our specific heat of our substance or our sample, in this case iron, but we always know the specific heat of water. So let's say we didn't know what was in there. We wouldn't even be able to do this whole calculation that we just did. We would have to do it for the water. So let's come down here and do that same thing, but now for the water. So in this case, Q equals M, our mass of water, is 175 grams. So 175 grams times the specific heat of water, 4.18 joules per gram degrees Celsius. And then our temperature change, in this case, much simpler. Our final temperature is 29 degrees. Our initial temperature is 25 degrees Celsius. So that gives me 175 grams times 4.18 joules per gram degrees Celsius times 4 degrees Celsius. And then if I go plug that into my calculator, 175 times 4.18 times 4 is 29.26, which is about the same as what we got here. So in this case, this would be positive. Oh, stop doing that. In this case, this would be positive because this is the energy. Nope, not the energy. I mean, it is energy, but heat energy gained by the water. So that's the heat that is gained by the water. These numbers should be approximately the same because in theory, all of the energy that's transferred from the iron to the water, that's the only place it goes. Now, this, for example, might be a little bit higher because maybe there's heat coming in from outside that is not fully insulated. Or if it's lower, maybe heat is getting lost from the container. And that would mean that there's another factor that we couldn't control. It often happens in calorimetry experiments. But yes, in theory, it should be the exact same amount of energy transferred between the two substances. Key things to remember, if you noticed, when I did this equation, every single one of these variables was related to the iron. So if I'm calculating energy for the iron, everything here has to be for the iron. If I'm calculating energy for the water, then all of these variables have to be related to the water. You can't mix and match like the mass from the water and then the specific heat from the iron and then the temperature change from the water. It doesn't work like that. It all has to be related to the same substance. So that's a really, really important thing when you're doing these equations. So now I have some practice problems for you. I want you guys to try this on your own.